So hi guys, Assalamualaikum warahmatullahi wabarakatuh. And today for video presentation CHM260, we will presenting about gas chromatography or GC. So first of all, our group member consists of 4 people, which is the first one, Muhammad Iqbal Haris. The second one, which is me, Syed Iman Bahtiar bin Syed Azman. The third one is Zarul Mukris. And the fourth one is Cik Syafiq Aidil. Moving on to the introduction. So what is gas chromatography? Gas chromatography or GC is an analytical chemistry technique that separates, identifies and quantifies volatile compounds in a mixture by vaporizing them and passing them through a heated column with a carrier gas, or we can call it as a mobile phase, over a stationary phase, with a different component separating based on their boiling points and interactions, producing a chromatogram. Gas chromatography is widely used in environmental analysis, food and fragrance testing, forensics, petrochemical studies, and also pharmaceutical quality control. It offers high sensitivity, excellent resolution, and also rapid analysis time. Moreover, the objective of gas chromatography experiment is to determine the retention times, TR of N-butanol and also 2-propanol. The next one, or the second one, is to identify the components present in a standard mixture based on the retention time.
Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. My name is Zarul Mukris bin Ahmad, and in this slide, I'm gonna explain about the methodology that we use to achieve all the result and also to achieve all the objective for this experiment. Here, we can see a fully labeled block diagram of the gas chromatography instrument. The next one, I'm gonna explain and state a step-by-step of how the gas chromatography instrument will work. The process starts with a carrier gas tank, which will provide an inert gas such as nitrogen or helium. The next one, the gas will go through the pressure regulator and flow controller. The next one, the sample will introduce through the sample injection port. And the next one, the mixture then move into the GC column, which we can see based on the block diagram. It is in the inside of the column oven. The next one, once separated, the compound will reach the detector, which in this analysis is a flame ionization detector, or we known as FID. And lastly, these signals are sent to the data system or computer, where they are processed and displayed as a chromatogram. Next, I'm gonna names and function of each component of the gas chromatography instrument that we have seen in the previous slide. The first one, we have a carrier gas tank, which supplies an inert carrier gases such as helium or nitrogen that acts as the mobile phase. Next, it will transport the vaporized sample through the GC column. The second one, we have a pressure regulator and flow controller. It will regulate the pressure of the carrier gas from the cylinder or carrier gas tank. It also will maintain a constant and controlled gas flow rate for reproducible analysis. The third one, we have a sample injection port. In this component, it will introduce the sample into the GC system. It also will rapidly vaporizes the sample to allow efficient transfer into the column. The fourth one, we have a GC column, which located inside the column oven. In this component, it contains the stationary phase, where separation of components will be occur. It will separate compound based on the volatility and interaction with the stationary phase. The fifth one, we have a detector, or in this analysis, we known as a FID. It will detect organic compound by ionization in a hydrogen air flame. It also will produce an electrical signal proportional to analyte concentration. And lastly, we have a data system, or in this analysis, we have a computer. It will record and process a signal from the detector. It also will display chromatogram for identification and quantification of the compound.
For the result, starting with our controls at 70 degrees Celsius, we ran the pure compounds individually to establish a baseline. 2-propanol eluted at 2.724 minutes, while N-butanol significantly longer, eluting at 6.043 minutes. When we ran the standard mixture at the same temperature, we saw two distant peaks. The first appeared at 2.692 minutes and the second at 5.903 minutes. These values align closely with our individual standards, confirming the order of elution. As we increase the column temperature, look at what happened to those retention times. At 100 degrees Celsius, the peaks shifted much earlier to 2.269 and 3.294 minutes. By the time we reached 140 degrees Celsius, both compounds exited the column in record time, the first at 1.52 and the second at 2.25 minutes. Finally, notice the gap between the two numbers in the right column. At 70 degrees Celsius, there is a massive 3.2 minute difference between the compounds. By 140 degrees Celsius, that difference has shrunk to just 0.27 minutes, meaning the peaks are much closer together. For the discussion, in peak identification, peaks were identified by matching the retention time of individual standards, which are 2-propanol and N-butanol, to the peaks in the mixture at 70 degrees Celsius. 2-propanol elutes first, which is at 2.7 minutes due to its lower boiling point, while N-butanol elutes second at 6.0 minutes. For the effects on retention time, increasing temperature significantly reduces the retention time from 5.9 minutes at 7 degrees Celsius to 2.2 minutes at 140 degrees Celsius. This means that the higher heat increases analyte vapor pressure, causing molecules to spend more time in the mobile phase and travel faster. Lastly, the effects on resolution. Reducing temperature improves resolution. For instance, at 70 degrees Celsius, peaks are widely separated at 3.211 minutes. Next, increasing temperature compromises resolution. At 140 degrees Celsius, the gap narrows down to 0.273 minutes, risking peak overlap. In short, lower temperatures provide better separation, while higher temperature provide faster results.
For the conclusion, the objective of this experiment was successfully achieved through the qualitative analysis of alcohol, standards and mixtures using gas chromatography. By comparing the retention time, the two primary components in the standard mixture were identified as 2-propanol and N-butanol under the initial temperature program of 70 to 140 degrees Celsius. The individual standards for 2-propanol and N-butanol exhibit retention time of 2.724 minutes and 6.043 minutes, respectively. These values align closely with the peaks observed in the standard mixture at 2.692 minutes and 5.903 minutes, confirming the identifier of the substances based on their characteristic elution behavior. Furthermore, the experiment demonstrates the significant impact of oven temperature on the separation process. When the temperature program was increased to 100 to 140 degrees Celsius, for 100 degrees Celsius, the retention time for the component in the standard mixture decreased to 2.269 minutes. For 2-propanol, while for N-butanol is 3.294 minutes. And next, for temperature 140 degrees Celsius, the peak of standard mixture have closer gap between each other, which are 2-propanol and N-butanol compared to 70 degrees Celsius and 100 degrees Celsius. It makes the reduction time become more faster, which are 1.952 for 2-propanol and 2.225 for N-butanol. This shift confirms that higher temperature reduces the interaction time between the analytes and the stationary phase, leading to faster elution. Overall, the study highlights that while higher temperature can speed up analysis, precise temperature control is essential for maintaining proper separation and reliable identification of chemical compound within a mixture.